Yeah, so rate of reaction basically means that whenever you have a reaction going on, we might want to measure how fast or slow the reaction is happening. Why is that important? Because usually when we do these reactions, we want to figure out how much of the product is made, and usually time is of the essence. For example, in industry, then you have people who are helping you do the reaction. You have labor, you have to pay for power, the electricity charges and all that. You have to keep the machines running for a certain amount of time, and you don't want to increase the time without damaging the machine or obviously risking things. So that is why measuring time and how fast or slow the reaction is happening is important. Similarly, if you have some targets, for example, if you're in a cement manufacturing plant and you're like, okay, how much cement has been made, then it is possible that there is some byproduct being made as well. But you are only interested in the cement being made. So you would like to know how much cement is made in how much time so that you can go and sell that cement and make some profit, right? So rate of reaction is important because it is closely related to the economic activities that are related to these chemical processes. In the lab, we have similar things, but at a smaller scale. So that is why rate of reaction is an important aspect of this practical chemistry. So what exactly do we measure here? We measure two things. One is then whenever you have a reaction, you obviously want to measure the time taken to do the reaction. So this is your change in time. So this triangle means delta, and delta is change. So the change in time that has happened for any reaction to occur. And secondly, you are going to measure the output that is made. So that will be your change in the output that you have. So that output can be of different ways. For example, if there's a reaction in which a gas is being made, an example would be calcium carbonate that you're breaking down, for example, using heat. So you're giving it heat and you're getting calcium oxide and carbon dioxide. Notice that the same delta symbol has two different meanings. When it's written over here, that means heat. So this is heat. I mean, it's written like that. That means the change in whatever thing it's written with. So here what's happening is that you have this solid, and this is the gas. So obviously gas is being given off. So you can be like, okay, I can collect the gas. So you can do this reaction in a way that, okay, I have a conical flask, and in that flask you have this calcium carbonate powder, and you're heating it. So when you heat it, some gas will be evolved. You collect that gas. You are like, okay, I will collect that gas in a gas syringe, and this syringe has some markings on it, so you can easily measure it. And now you obviously have to seal this container so the gas goes right into the tube. So here you're collecting the gas. So this is your change in volume of gas that you're measuring with respect to time. So this thing you can do by first making a table. So you take some time, and on the other side, you're taking the volume. So you're like, okay, at 0 seconds, so the unit is usually written in parentheses. So at 0 seconds, the volume, which could be in centimeter cube, for example, you're like, okay, at 0 seconds, 0 cm cube has been collected. At 10 seconds, 2 centimeters collected. At 20 seconds, 2.8 centimeter cube collected. At 30 seconds, 3.4 centimeters cubes collected. At 40 seconds, you're like, okay, 3.6 has been collected. And at 50 seconds, it is still 3.6. At 60 seconds, it's still 3.6. So what is this showing? Number one, it's showing the change. So let's see the change on the side. So the delta, which is supposed to be the change. So from 0 to 2, the change is of 2 centimeters cube for the same 10 seconds. But for the next 10 seconds, the change is of 0.8. For the next 10 seconds, the change is of 0.6. For the next 10 seconds, changes of 0.2. For the next 10 seconds, the change is 0 and 0. This shows that for the same 10 seconds, my reaction produced 2.0 centimeter cube initially, but in the next it produced 0.8, in the next it produced 0.6, in the next it produced 0.2. So this tells me that the rate is decreasing. How do I know that? I'm comparing the volume produced in the time that it took to do that. And when I divide them, I'm able to figure out how much my rate is. In O levels or IGCSE, we don't do much calculations. What we do instead is we take the table and we just draw it on a graph. So you can take this thing, put it on a graph. So at 0, it is 0. At 10, it is 2. Let me just put it like this. Okay, this is 1. This is 1. This is 2. This is 3, and so on. This is 4. Okay, so let's put it. So at 0, it is 0. At 10, it is 2. At 20, it is what? 2.8. At 30, it is 3.4. At 40, it is 3.6. At 50, it is 3.6. At 60, it is also 3.6. Now let me join these. So if I were to join this using a smooth line, so we usually try to make a smooth line, then there are two parts of this. Number one, over here, there's a high gradient. The line is very steep. That means there's a high rate. The gradient tells me the rate. And you can see that the gradient slows down, which means the reaction is slowing down. And over here, there is zero gradient. This is a horizontal line. That means the rate is 0 or reaction is complete. When we say reaction is complete, it means there is no product that is going to be made now. All the product that could be made right now, it has been made. So it has produced everything that it could in the time that you had. So you cannot produce any more gas from this same calcium carbonate. Why? Because maybe all the calcium carbonate has been used up. So that is why you cannot produce any more of it. So there are two ways, as you can see, of measuring the rate. Number one, you take the output, which was volume in this case, and you measure the gradient or the slope, the change. And then you're able to see that if the change is fast, then the reaction is fast. And if the change is slow, the reaction is slow. And if there is no change, which means the gradient is 0, then the reaction is complete and there is no change. Okay. So that is your rate of reaction. Now, in the same reaction, another thing we can do is that instead of measuring volume, we can be like, okay, we're going to do the same reaction. We're going to take a conical flask. We're going to put calcium carbonate in here. We're going to heat it, but we're not going to collect the gas. But we still want to put cotton wool here because we don't want air to come in. Okay. Now what happens? When you heat it up, carbon dioxide just goes out. What that means is that your volume, obviously, you're not able to collect the gas or measure the volume of gas. Obviously, you're not collecting it. So what we can change is that as you heat it up, the mass will reduce. Why? Because the gas is going to go out. So the mass of the thing is going to fall down. So in this case, what we can do is we can measure the mass. So for that, we can put this thing on a balance and we can measure the change in mass. Again, we will make a new table. So for this table, we are going to take time on one side and we're going to take mass on one side. So it could be grams. So let's suppose in this case, initially at 0 seconds, our mass was 20 grams. But after 10 seconds, the mass was 14 grams. After another 10 seconds, which means total 20 seconds, the mass was 10 grams. After 30, it was 8. After 40, it was 8. And after 50, it was also 8. So what does this show? This is showing that the reaction is complete because there is no change. Now let me graph it. If I wanted to use the delta thing, I can do that. I can be like, okay, here it has fallen down by 6. Here it has fallen down by 4. Then it went down by 2 and then 0. That means the rate is decreasing. If I were to draw the graph here, then again, I will do the same thing. Time on one axis, mass on the other axis. I can write it like this, that mass and gram like this as a slash, or I can simply put this in a parentheses. Then I can be like, okay, 0, 10, 20, 30, 40, 50. And on this side, I have, let's suppose this is 10, this is 20. And I'm going to take the values. Okay, at 0, this is 20. At 10, it is 14. At 20, this is 10. At 30, it is 8. At 40, it is 8. And then it is 8 again. So if I were to draw the graph now, I will see it like this. Again, there is a high gradient here and there is low gradient here, as you can see. So this is showing that the gradient is falling down. And over here, the gradient is 0. So that means the reaction is complete. When is it complete? The moment it becomes a horizontal line. So that is when I know the reaction is complete. So this is the first part of this chapter, that how you can measure the rate. So for example, if you're getting a gas, then you can either collect the gas and measure that, or you can just let the gas go away and measure the mass. So what factors can you use? So obviously the first thing that you always have to measure is time. So time is usually measured in seconds. You always have to do that. So obviously you will need stopwatch or something for that. The second thing that you can measure is your change in output, and that could be change in mass, change in volume, change in pH, that could be change in temperature. So units will vary. So for mass, you can have grams, for volume, cm cube or dm cube is good. For pH, obviously, it is a ratio, it doesn't have a unit. And for temperature, you can have degrees Celsius. So all of these things tell me how the temperature, how the volume, how the pH, all of that changes as you do the reaction. And obviously, when you do that, things will make graphs and you can put them on a table and you can do all sorts of calculations with that. Okay, so that is how you measure the rate of reaction. You keep any reaction and you're like, okay, what is changing in this reaction? If it's not changing, then you cannot measure it. So you're like, okay, what is changing in this reaction? And then you measure the change. It's very important that you measure the change. So usually, so if you have a volume of gas, then we collect the gas. So we will have to collect the gas in gas syringe mostly. But if you're changing change in mass, then you will use a balance, okay, to do that. If you're changing temperature, then you will use a thermometer to do this. So all of this depends on what factor is changing and how you're able to measure it. So I'll just tell you about a few ways examiner uses this. So there is obviously this one in which you have a gas that is being collected in a gas syringe. And this means that you are measuring it based on the volume of gas. Okay. Similarly, we sometimes have things where you have balance, as I've shown you. So this balance tells me the change in mass. Okay, so there's a change in mass. Similarly, to measure the change in temperature, we sometimes have this thing and we're heating it up or whatever, and we have a thermometer, and that thermometer tells us what the values are. So in this case, your graph or the table will be time in seconds and your volume in cm cube, and then you will put the values here. In this case, you will have time in seconds and you will have mass, which will be in grams, and you will take the values here. In this case, you will have time in seconds and you will have temperature in degrees Celsius on the side, and then you will measure that. So the table always goes like that. Now, some important points to remember for this is that, for example, so that's the thing, whenever you have any change in mass or the rate is changing, you use one of these ways of figuring out or setting up the equation, setting up the reaction setup, and then you use that to figure out, okay, how the reaction is changing. Now, the second thing, why does this happen? So the first part of the chapter is all about measuring and using graphs or identifying what you can measure. So for example, in the case of this thing, when the volume is changing, obviously the graph will be something like this. It will start at 0 and go up. Why? Because the volume is going to increase at 0. So volume here you in cm cube, and you have time here in seconds, and it's going to increase from 0. When the case of mass, it's not going to start from 0. It's going to start from some initial value, because mass will not be 0 regardless of what reaction happens. So what happens is that it usually starts from some point and goes down to a fixed value. It never comes down to 0 because mass again will not be 0. You still have the equipment which has a mass, or you might have some solid that is left over which has a mass, or some impurity and all that, usually doesn't go to zero. That is one you have to remember. All right, so moving on, why does all of this happen? Why does the rate decrease? Why does the gradient slow down? Why does the reaction not happen anymore after we say that it's complete? Why do we get horizontal line? So all of these things have their answers, and the answers are pretty simple. There's this thing called collision theory. So collision theory answers all of these questions for us. And what collision theory says is that first of all, you have any equation, you will have reactants and you will have products. So reactants will change and make products. These reactants, these particles are going to collide with each other. So the idea is that these particles will collide with each other. And when they collide, and if that collision is strong enough, then they will make products. So for example, if you are taking a simple example like H2 and O2, and they're making water. So if I balance this, then this hydrogen molecule should collide with oxygen molecule with enough energy that it produces water. So first of all, when they collide, these collisions, all of the collisions are not going to make water. The only collisions that will make water are the collisions between these reactants. Oxygen particles, if they keep on colliding with other oxygen, it won't help. Hydrogen colliding with hydrogen won't help. It is only when hydrogen collides with oxygen that it reacts. Secondly, these collisions must have some basic energy. In the last chapter, we talked about activation energy. So when these collisions happen with activation energy, the minimum energy required to start the reaction, only then will they produce the product. So this kind of collision we call a successful collision. Some teachers call it fruitful collision. I don't know what that means. It simply means a successful collision, a collision that bears fruit, that makes the product. I don't like that term though. So successful collision simply means a collision between reactants. So that's the important thing. And second, with enough energy. So they must have energy that is greater or equal to the activation energy. If you don't have that, then it is not possible for the reaction to complete. Now, if you're somebody who's doing these reactions, then what do you want? You want more successful collisions. You don't want unsuccessful collisions. You want the reaction to continue and be happening in a suitable manner. Also, if you want a reaction to be faster, then you want more collisions in the same amount of time. And if you want the reaction to be slower, which does happen sometimes, we want some reaction to be slowed down, then you want the collisions to be slower. You want them to be lesser in the same amount of time. So that means when we want to have a high rate, we want more collisions per unit time. And when we want a low rate, we want less collisions per unit time. And that is what successful collisions would mean. So what factors affect it? So all of it has to be explained with collision. I don't know how to spell it. So the first thing is temperature. What does temperature do to collisions? So here's the thing. Temperature gives particles kinetic energy. When they have high kinetic energy, they collide more. And when they collide more, they do more successful collisions. And when there are more successful collisions, the rate is high. Okay, so there's no need to write that. So we just want more successful collisions, and for that, temperature will give it more kinetic energy. The second important aspect here is the concentration. Concentration is how many particles you have in how much volume. So this is particles per volume. So if I have more particles, they will collide more. Simple. If you have more particles, they will be colliding more and they will have a higher chance of colliding, higher rate. Simple. Then we have catalyst. What catalyst does is it reduces the activation energy. Now, Let's suppose initially particles did not have that much energy, but now they qualify. So an example of that would be that let's suppose you want to take part in a competition and the competition ticket is for, let's suppose, 1,000 rupees. Now there are 10 people in the line who want to take part in that competition, but only 4 people have 1,000 or more and 6 people don't have that much. Then that means only 4 people will be able to take part in the reaction in the competition. Simple, because they don't have enough money. Now let's suppose the company comes up with, okay, for now we are going to reduce the price to 800. Now people who did not have 1,000 but had 800, firstly they weren't able to take part in the reaction or the competition. But now, because the ticket amount has been reduced, they can take part in this. So, agar pehle 4 log kar rahe the, now it's possible that now you have 6 people competing. And what has happened? It's not that they had somehow gotten more money. It was simply that the money they had, suddenly it was enough for them to take part in the competition. Just like that, when you're doing this reactions, particles have their energy, but they need their energy to be greater or equal to the activation energy. Now, if you reduce the activation energy, then the particle that did not have that much energy initially, but now it does, now it qualifies, that will also take part in the collision, that will also take part in the reaction. And that is how catalyst speeds up the reaction. It makes more collisions possible because it reduces the activation energy. And now more particles qualify. Now, there are 2 other factors that affect the rate of collision. First is only for solids, and the second is only for gases. The gases one is called pressure. And this is for gases only. What happens? When you increase the pressure, gas particles are able to come close to each other and they collide. It's not possible in solid because if you apply more pressure on the solid, then it will simply compress more, but the particles will not be able to come any more closer than they were. There will be a very small change there. But when you increase the pressure of gas, because particles are free to move around, they come and collide with each other. Similarly, if you have surface area means that particles are exposed. So for example, if I have one block here, then I want air to react with it, then air can collide here, air can collide here, air can collide here. That's it. But if I slice it like that, if I slice the cube into 2 smaller cubes, now what is possible? So I have 2 smaller cubes now, and now air is able to collide here, here, which it was able to do before, or here, which was able to do before, or here. But now there is this new side on both of them that wasn't available to air before. So now air is able to collide here. So there is more area exposed to the surroundings where the reaction can occur. So the smaller particle you have, so smaller particles have higher surface area, which means they have more exposed area where the reaction can occur. So that is why this is only for solids. So this is solids only. And that is how they're able to collide, and that is how they're able to speed up the chemical reaction. Now remember, whenever you are going to talk about this, do not forget how collision theory depends on time. So the more collisions happen in the same time, the higher the rate of reaction. Okay, and that is exactly how we speed up the chemical reaction. So that's it for this chapter.